In the last video, we used Gaussian elimination to solve a system of linear equations. And it turned out that that particular system had a unique solution. This is not always the case, and as it turns out, what happens is one of the following three things. Either the system will have no solution, or it will have a unique solution, or it will have infinitely many solutions. And to decide between these three possibilities, we'll need to know what the rank of a matrix is. So let's first see a few examples of these possibilities, and then we're going to define the rank of a matrix and see how this rank enables us to decide which of these possibilities happens. So let's suppose we have a system of two linear equations and two unknowns. Let's say ax plus by equals e, cx plus dy equals f. And let's assume that at least one of a and b is non-zero, because if both a is 0 and b is 0, then either e is 0 and we can ignore this equation, or e is non-zero and the system has no solution. And similarly, let's assume that at least one of c and d is non-zero. But then, since at least one of a and b is non-zero, the equation ax plus by is equal to e represents a line in the Cartesian plane. And the same for the equation cx plus dy equals f. And in general, two lines have exactly one common point. And this common point is going to be the solution of the system. But it may happen that these two lines are parallel, and so there is no common point and no solution. Or it may even happen that these two lines are identical, in which case we will have infinitely many solutions. And in general, if we are given a system of m linear equations in n unknowns, then exactly one of these three things happens. Either we have a unique solution, or we have no solution, and we say that the system is inconsistent, or we have infinitely many solutions. So let's see an example. Suppose we are asked to solve the following system of linear equations using Gaussian elimination. So we start by building the augmented matrix. And then we need to perform row operations to bring it into row echelon form. So what we can do, so if you remember in the last video, we started by switching row 1, row 2 with row 1 to bring the 1 on top. So let's see another way to do that. So another way to make this entry 0 is to first multiply this row by 2 and then subtract row 1 from row 2. So what we do, we change row 2 to twice row 2 minus row 1. And similarly, what shall we do with row 3? We can multiply this by 2 and then subtract 3 times this row from this one. So row 3 is changed to twice row 3 minus 3 times row 1. And if we do the calculations, this is what we get. And now we can add row 2 to row 3 to get it into row echelon form. But now this system is inconsistent, because what is this last equation? It tells us that 0x plus 0y plus 0z is equal to minus 2, which is impossible. Now let's try to solve a very similar system. The only difference is that I change this, instead of being equal to 0, I now demand it to be equal to 1. Again, I build the augmented matrix. I do essentially the same operations as before, but now the last entry here is 0 instead of minus 2. And this system has solutions, because the last equation is trivially satisfied. We start from the bottom non-zero row. We want to solve y plus 3z equals to 1. We can pick z to be anything, let's call it t. And then the second equation gives that y must be 1 minus 3t, because we have that y plus 3t must be equal to 1. And then we can back substitute both y and z to get 2x plus y, which is 1 minus 3t, minus z, which is minus t, equal to 1, which gives x equals to t. So every triple of the form x, y, z equal to 2t, 1 minus 3t, t is a solution. So here we get infinitely many solutions, one for each particular value of t. Note that in both the previous example, and in which we had no solution, and this example in which we have infinitely many solutions, if we just look at the part of the matrix A, we have 2 non-zero rows, but 3 unknowns. And it turns out that this is the important point which make these systems to either have no solutions or infinitely many solutions. And this motivates the following definition. So we say that the rank of a matrix, which denoted by rank of A, is the number of non-zero rows of A when converted to row echelon form. Actually, we need to be a bit careful here. We need to check that rank of A is well defined. And why do we need to check this? Well, we have mentioned that A can have several distinct row echelon forms. So we need to check that if we have 2 different row echelon forms of A, they really do have the same number of non-zero rows. And this is indeed the case, so rank of A is indeed well defined, but we are not going to prove it. Okay, so now let's go back to our previous 2 examples. The first example had this augmented matrix, the second example had this augmented matrix. And they were converted to these 2 row echelon forms. In the first one, the rank of A is equal to 2 because it has 2 non-zero rows. And the rank of the augmented matrix is equal to 3 because here this is also a non-zero row for the augmented matrix. So it's a 0 row for the initial matrix, but a non-zero row for the augmented one. And in this particular example, the rank of A and the rank of the augmented matrix is equal to 2. Now our next theorem says the following. Suppose we have the system of linear equations, m linear equations in n unknowns. So A is an m times n matrix. Then it tells us something about the rank of A. It tells us that it is less than or equal to each of these 3 numbers. It says that it's less than or equal to the rank of the augmented matrix. This is not difficult to see. Just convert both of them to row echelon forms using the same row operations. And then observe that for every row, if it's a non-zero row of A, then it's a non-zero row of the augmented matrix. But if it is a 0 row of A, then it might be a 0 row of the augmented matrix, it might be a non-zero row. So the rank of A must be less than or equal to the rank of the augmented matrix. Of course, the rank of A is less than or equal to m, since A has at most m rows. And of course, the rank of A must be less than or equal to n, which is the number of columns of A. And the reason for this is that every non-zero row of A has a leading digit. And this leading digit must be in a different column. So there are at most 10 of them. Okay, and now the important part of the theorem. So either the rank of A is equal to the rank of the augmented matrix, and then we have 2 subcases. Either both ranks are equal to n, the number of the unknowns, and then the system has a unique solution, or both of them are equal, but they are less than the number of the unknowns. And in this case, the system has infinitely many solutions. And the final case is that the rank of A is less than the rank of the augmented matrix, in which case the system is inconsistent. So to recap, for the system to have a unique solution, we need the rank of A to be equal to the rank of the augmented matrix and be equal to the number of unknowns. Otherwise, if the rank of A and the augmented matrix are equal, then the system has infinitely many solutions, if they are less than n, or If the rank of the matrix is less than the rank of the augmented matrix, then the system is inconsistent.